Hello friends, in this video we are going to discuss about the continuity equation in a semiconductor. For that, let us consider a block of semiconductor. This is a block of semiconductor that we have taken, and in this block of semiconductor let us denote this axis. This is the 3D diagram of semiconductor block. So let us denote the direction in this semiconductor. Let us say that this is the x-axis, this is the z-axis, and this is the y-axis. That means this direction in the x is the x direction, this is the z direction, and this is the y direction. Now let us consider that this has a differential volume. That means let us consider the length in the y-axis is denoted by dy in this way, and in the direction of x-axis the length of the semiconductor block is dx, and in the z direction the length will be dz. So we can say that it will have a differential volume of dx, dy, and dz. Now assume that, now let us consider that a one-dimensional whole particle flux is entering the volume at x. That means a one-dimensional whole flux that is entering from this plane, and we have denoted that considering that one-dimensional whole particle flux is entering the volume at x and is leaving the volume at x plus dx. That means the whole particle flux is entering this volume at this point. So at this point plane, so this is x, and this point is x plus dx. So the whole particle flux will leave this volume at this point in this way. Now let us denote that the whole particle flux at x is Fp x plus, and the whole particle flux that will leave the volume, or the whole particle flux at x plus dx at this point is Fpx x plus dx this one. So we can say that f of px x plus, this is the whole particle flux at x, and f px at x plus dx plus is the whole particle flux at x plus. This is the total scenario right now, and if we find what is the whole particle flux means. Whole particle flux, it means that number of holes per unit area per unit second. This is the meaning of whole particle flux. Now, from this scenario, we can say that at x point, the whole particle flux is F plus Px x, and at x equals to x plus dx point, that is this point, the whole particle flux is given by Fpx x plus dx plus. So we can say that the Fpx x plus dx plus, that is the whole particle flux at x plus dx, can be written as f of px x plus del of fpx plus by del x into dx. So this term denotes the rate of change of whole particle flux inside the volume. Let us denote this equation as 1. From this equation 1, we can say that if p x plus dx minus f px x plus is equals to del of fpx by del x into dx. Now, this equation can also be written in this form if we take fpx first minus f of px x plus dx plus, it will be equals to minus del of fpx plus dx and into. So the left hand side of the equation 2, that is this part, can be written as this is the net increase or net change in the whole particle flux inside the volume, inside the differential volume, due to the component of whole flux that is flowing through the x direction. Now similarly, we can find the whole particle flux increment within the differential volume. So this is the net increase or net change in the whole particle flux inside the differential volume in the x direction. So let us find the net increment or net increase in the number of holes per unit time within the differential volume, within the differential volume, due to all the direction x, y and z. We can write f px x plus minus f px plus x plus dx into dy dz equals to minus del fp x plus del of x dx dy dz this way. So we can write, let us name this equation as equation 2. So from this equation we can say that this equation can be written in the form or with respect to the time, because it is whole per unit time, number of whole increment per unit time. So we can write del P by del T, where P is the concentration, into dx dy dz equals to minus del fpx plus del x dx dy dz. Now from this equation we can say that if the fpx x plus is greater than f px x plus dx plus, if this happens, then from equation 2 we can say that there will be net increase in the number of holes, in the number of holes in the differential volume, in the differential volume element with time. Similarly, we can say that if px of x plus is less than fpx of x plus dx plus, then we can say that there will net decrease in the number of holes in the differential volume element with time. Now this increment and decrement that is happening inside the differential volume, the reason behind this is the generation of carriers, and another is the recombination of carriers. Due to these two phenomena, there can be a generation and recombination of carriers, and due to which there can be increment or decrement in the number of carriers inside the differential volume. Now, if there is a generation of carriers, then there must be some generation rate. Let us assume that Gp is the generation rate within the volume dx, dy, dz. So this is the generation rate of carriers. Similarly, if there is a recombination rate, the recombination rate, due to the recombination rate, always the volume, inside the volume there must be the decreasement or decrement of carriers. So we can say the recombination rate can be written as minus, for holes we can say minus p by tau pt dx dy into z. And this minus sign comes because due to the recombination, the concentration decreases with time. So we can write the total equation, or we can modify the equation 3. If this is the equation 3, then we can modify this equation using these informations of generation and recombination, like this. So we can write the equation 3 as follows: del P by del T within the volume del X, del Y, del Z. This is the differential volume. So it will be minus del Fpx plus by del X into the volume, that is del X, del Y, del Z, plus then comes the generation factor or generation rate Gp, that is dx, dy, dz. Then comes the recombination lifetime or recombination rate, that is for holes it will be p by tau pt, where tau pt is the recombination carrier lifetime, recombination lifetime of the holes. So there will be dx, dy, dz for the elemental volume. So let us denote this equation for 4. Now from this equation we can say that the first term, this is the first term that I am talking about. This first term gives, what does it give? It gives the net increase in the number of holes per unit time within the differential volume dx, dy, dz. Now we come for the second part. The second part, the second term, this second term will give the net increase in the number of holes per unit time due to the generation of holes within the differential volume. Similarly, this third term will give the net decrease in the number of volume in the number of holes per unit time due to recombination. That's why there is a minus sign before the third term, because there is a decreasement of the number of holes. Now the recombination rate, that is in this equation, the recombination rate is given by this term. This is the recombination rate, where tau pt includes the thermal equilibrium. This tau pt is nothing but the thermal equilibrium carrier lifetime or the excess carrier lifetime. Now if I divide this whole equation 4 by dx, dy, dz, that means Dividing equation 4 by dx, dy, dz, we will get an equation like this: del p of del t will be equals to minus del fpx plus by del x plus gp minus p divided by tau pt. So we have got this equation. This equation is called the continuity equation for holes. Similarly, we can find the continuity equation for the electrons, and it will be written as del nt, where n is the concentration of electrons, by minus del of fn x plus by del x plus g n, that is the generation rate of the electrons, and the recombination rate n by tau of nt, where tau of nt is the recombination real lifetime of electrons. This will be the continuity equation for electrons. So this is all about the continuity equation for holes and electrons inside the semiconductor. Thank you.